Ladies and gentlemen, not too long ago, we took a look at SQL, the Structured Query Language. In that video, we took a look at, the basic to somewhat intermediate operations with SQL, and we ended off by saying that there was a lot more to SQL that we didn't have a chance to look at. So today, let's go and talk about some of these more complicated things. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. So, we're going to go into intermediate to advanced SQL today, and our just sort of general overall theme here is the ability to combine tables. Clearly, this is something we've already done, right? We've done a simple version of this back then. When you say select, you can have multiple tables, and this basically creates what is known as a Cartesian product. One row of one table is matched to every single row of our second table. Then the second row of the first table is matched to every single row again. This creates a very large result. The number of rows you have is essentially, the number of rows on the first table multiplied by the number of rows on the second. So that works, and using something like a where statement, we can filter things down to only what is relevant. However, as it turns out, that is not the only way to bring results from multiple tables together. And today, we're going to focus on a whole bunch of other ways to achieve the same thing. Some, if not all of these ways, provide additional expressive power. That is, there's certain things you can do using these methods we are about to see that you couldn't by just taking two tables and just smooshing them together. So yeah, today's video is going to come to you in three parts. Firstly, we're going to start simple-ish by taking a look at multiple queries. The idea is that you can do multiple queries and combine their answers together. So yeah, that's the most basic. After that, we're going to move on to the concept of a join. Joins are pretty interesting because there are ways in which you can bring tables together that are not Cartesian products. You may get more rows, you may get less rows. So yeah, there's a lot of dynamism in this. Finally, we'll move on to nested queries. Now, this is the one that is crazy powerful because you can have a small query on the inside that gives you some result and a larger query on the outside that operates on that result. So yeah, very interesting set of things you can do. Let's get started with our first one. Firstly, multiple queries. Now, this one definitely gives you some things that, traditionally you cannot do. For example, if you select on multiple tables, it's just going to add more and more columns for you within your result set. However, there is no notion of basically injecting things from two tables onto the same set of columns. You will need multiple queries to do this. So yeah, with this in mind, let's take a look at some ways in which you can, build columns that contain information from multiple tables. Now, just a quick note here, we are working with SQLite, which is of course, one particular flavor of SQL, and we're executing all this within a program called SQLite Browser. So all downloads will be in the video description, right? You'll be able to find this particular database that I will be using, as well as a download link to the SQLite Browser. So yeah, you pop open the video description, get what you need, and follow along. Before we begin, let's take a quick look at what we actually have here to play with. Now, in this particular file, which we will use throughout this entire episode, we have 4 tables. So they are as follows. Last time we did some sort of a grocery store kind of thing, right? So we're going to continue along the same lines for this one. So we have a table of fruits, right? Fruit and its price. We're going to be using this table as well as this one, right? These two tables for our first part where we bring multiple tables together. So over here we have high demand items, these are the things. We have low stock items, these are the things. So we'll see how we can bring them together. Now, the last table here, tags, this is also linked to our fruits, right? And I think that will make a lot more sense later on when we start talking about joins. So for now, let's focus on this table here, high demand items, as well as this, low stock items. Look under the high demand items, right? You'll see that some of these items are actually overlapping with our low stock items, right? Candy being one of them. There are of course also items that are different, right? We've got bread in this table and no bread on this table, right? So yeah, just do take note of the properties of these two tables. As you can imagine from the name, the high demand items are the items that are both high in demand, and the low stock items are the ones that are running out. Since we have things in this order, what we can do is we can actually try and figure out some things, right? Let's say I'm deciding whether to restock or not. Well, I could use these two tables to help me. The easiest one, right, and we're going to switch into our Execute SQL tab now to do this. The most basic set of things we can order are, well, items from both tables. The items that are high in demand should be restocked so that the stock doesn't go too low. Obviously, the items that are low in stock should be restocked as well so we can, well, get the stocks back up. So essentially what we want is a combination of the two tables. The basic selection isn't too hard, right? I want to select, let's say, just the item from our high demand items. But how am I going to join this up with our second table, which can be queried like this: select item from low stock items, like so, right? So essentially we have two completely separate queries, right? And we're gonna have to somehow magically bring them together. Well, SQL allows you to do that by taking a union of our two tables. Watch what happens when I run this. We now have 9 rows, and it's actually a combination of our items from both sides. Now, this one is very, very interesting because unlike our selection statement that has multiple inputs, we are not creating an additional column. We're taking columns from here and we're joining it up with columns from here. So the mechanic here is something unique, is something different from what we've seen before. Now, do note that even though certain items were doubled up, I think just now I showed you that candy was doubled up across both these tables, you only see one copy of it here. That is a property of the union statement. When you say unioned across two queries, what happens is they're joined together and duplicates are removed. Now, you don't necessarily have to do that, right? If you want to keep the duplicates, you would say union all. Previously we had 9 rows. When I run this now, see, we have 11 rows now, and you can see that candy has been doubled up, as has snacks over here. So yeah, that would be the union statement. Of course, union is a term that comes from set theory, and if you recall your set theory from high school, you'll know that there are a couple of other things we could potentially put here. Let's say now, instead of, just being conservative and stocking up everything, perhaps I wanted to cut costs, and therefore only try to stock the items that urgently require restocking. In this case, I want items that are high in demand and low stock. That means they're gonna run out real quick. If that's the case, I want to look for an intersection. So I'll make a selection here and give me back the results that intersect with the second list. Again, the results are candy and snacks, right? These are the things that belong in both these tables. And in other words, these are the items that are urgently running out. I've got to restock them real quick. Let's do one more and we can sort of end off this part. You can of course also do set subtraction, set differencing. Let's say I wanted to do some advertising for the items, right? Definitely the high demand items are going to be easy to advertise, but I don't want to promote the items that are already low in stock in case the stock gets cleaned out. So I would say accept. This allows me to promote the high demand items that are not low in stock. This is what I have. What happens is, this gives you back some items, and what I want to do when I say accept is to take away items from here. That's why you don't see candy, you don't see snacks, even though they were part of the high demand items table. This, ladies and gentlemen, is combining multiple queries together in a nutshell. Not too difficult to understand, especially if you can recall your high school math, the whole union and intersection thing, right? With that, we can actually easily join together the results of multiple queries into one set of columns. Moving on again, let's talk about joins. Now, joins are pretty interesting in the sense that, technically, our normal Cartesian product is a kind of join. But as it turns out, depending on the kind of join you actually choose, you can have slightly different behavior when two tables come together. Your traditional Cartesian product way may have some limitations, and by using the correct kind of join, we can work around these. Now, there is something I want to point out. Right now we're using SQLite, And SQLite does actually have some limitations on what kind of joins you can do. As we progress with the episode, I will be telling you how I'm working around these problems, but do note that some of the things I'm doing are just working around the limitations of SQL. You don't strictly have to do this if you're using a different DBMS. So yeah, just to give you a heads up at this point, right, let's jump into the actual content. Before we start, let's take a look at the data we're going to be using for this part. Firstly, we have fruits. Now, these fruits are just a name associated with a price. On top of this, what I also have are tags. Now, tags here are pretty interesting because do note, a couple of special things here. Firstly, not every fruit has a tag. Certain fruits are without tags here. Some other fruits have multiple tags. And there are also fruits here that are not in the original list. So there's a lot of room for sort of weirdness to happen. Now, if I try and associate tags to fruits using sort of the most basic way, and that is to simply use a select statement, which looks something like this, notice that this will fail. Now, let's take a look at what's happening here. Essentially, I want to get in both tables, right? And I want to match the fruits, right, the fruit name, to the fruit name on the tags table. This is sort of the very typical way in which we can bring together multiple tables. But in this particular context, you will find that, well, that's not going to work very well, right? Let's run this and we'll see. Firstly, I only get 5 rows back. I have lost most of the actual fruits from the original table, so that is a problem. In addition to this, the fruits that don't actually have a price, right, the fruits that are out of stock, they don't appear here as well. Let's take a look at why this is so. Now, when we do a selection statement like this, what happens is our tables are coming together where, well, the foreign key on one table is matched to the primary key of another. Because we want a strict mapping between the two, what happens is rows that don't match, that means if it's missing from one table or the other, they're actually discarded, even though we sort of have half information here. We only pick the rows that strictly match, and as a result, we lose rows. That's why in the case of the fruits, well, you end up with less. Essentially, a selection like this gives you only the intersection between the two tables. The only rows you get back live here. These are the rows that are present on both tables. If you're only present in one and not the other, well, that information is lost. So clearly, this is not the way. Instead, we need some mechanism to bring the tables together, but retain the rows that have nothing in them. For this, what we'll do is a left join. And what I'm going to do is I'm just going to copy and paste what I have already. Instead of saying select from multiple tables, I'm going to say make a selection and do a left join using this other table. Now watch what happens when I run this. Now, notice, I keep everything from my fruits table, including the ones that don't actually have tags. The stuff from the tags table are simply being joined on. They're just being tagged on here, but the nice thing is because there are 2 tags for the grape, this row is actually doubled up, right? We actually get to see both of the tags, which is a really nice thing. To keep things simple, a left join is essentially keeping everything from the table on the left. In this context, left simply means the table you actually mentioned first, right? In other words, the table that you're not using for a join. I want to keep everything here, and then I want to bring in the contents of table B, where this condition is actually being fulfilled. That is why we get a result that looks something like this. Where there are rows common to both tables, they get brought together. Rows that do not have, any value in the second table, that's fine, we'll just leave it blank, but we'll keep the row around. Again, to sort of use the Venn diagram kind of look, it looks something like this. I will keep everything from table A, even if it isn't present in table B. Of course, if they're both present, that's great, we'll bring the information together. So that's great, but we're missing something. Notice that there are some fruits without prices. Those are still not here, so we have to do something different to bring them in. Now, instead of thinking of keeping the results that we have here in addition to, well, bringing in the fruits that don't have a price, let's try and just look at the opposite problem first. Let's keep all the tags around and join in the fruits regardless of whether they have a price or not. As you can imagine, what you really need here is a right join. Unfortunately, we do have a problem with SQLite here, and that is right and full outer joins are not supported by SQLite. But as it turns out, we can actually sort of make a small tweak, right? A left join and a right join are not all that different. You see, what we're trying to express here is a right join. That is, I want to keep the stuff on the right table, and then I want to tag on whatever is available on the left. But don't forget, this is the left table because we specify it first, this is the right table because we specify it second. If we can't do a right join, let's just flip the whole thing on its head. Let's make our table B the left table instead, table A the right table instead. Then, all we're doing is simply a left join. At the end of the day, you effectively get the same result. What I've done here is I've actually swapped these two tables around. Since I can't have tags on my right, then let's specify tags first so it comes out on the left, and then I can do a left join on fruits. Now I can run this, and look, my watermelon and papaya do hang around even though they do not actually have a price, right? But because they have a tag, they must hang around now. So do remember, what we're doing here really is, supposed to be a right join if we sort of flip these two things around, right? I have to do a left join here because SQLite only lets me do left joins. But yeah, the concept here is the same, right? So if I were to flip the two around, right, fruits, tags, right join, this should work. Of course, there is still the elephant in the room, right? How can we actually bring both of these together? Well, actually for this, right, all you need to do is a full join. We've seen how a left join works, we've seen how a right join works. Essentially, a full join means just bring these two tables together. It doesn't matter that they don't have anything in common for a particular row, just keep them around. Fill in null items like this as and when is required. Unfortunately, again, SQLite doesn't like this. Full outer joins are not supported, but again, we can work around this. For this to work, we're gonna have to think about the first part of this video. If you realize what we had previously, right, was this as well as this. And these two are in fact the two halves of the same query. At the end of the day, what we get back is the same, right? The name of the fruit, the price, the tag. Some of these things may be missing, but yeah, regardless, at the end of the day, these are two halves. So what we can do is we can simply bring them together using a union operation. There you go, when we run this, what we have is everything. Here's a fruit without a tag, that's fine. Here's a fruit with two tags, that's fine. Here's a fruit that's out of stock so it doesn't have a price, that's fine. We have everything now. Again, remember what we're doing here is we're trying to emulate the effect of a full join. In order to appreciate how and why this works, well, we just have to basically trace through the entire thought process. Our first half does a left join, and therefore we keep all the rows from table A. Our second query below gives us a right join, keeping all the rows from table B. Each one of these independently evaluates to something like this. We have empty rows filled in here and here. Well, we can simply combine these two tables together, right? And we'll basically have everything from every table. Of course, do note that certain of these rows are actually doubled up. That doesn't matter, SQL knows to remove duplicates, so well, we can simply bring it together, and yeah, you now have everything. This was your original table A, this is your table B. Basically, well, they have connected themselves together, eliminating duplicates. So yeah, this is just a simple union operation. This would be much simpler if SQLite actually allows you to do a full join, right? You can just, say a full join and you're done. But unfortunately, SQLite doesn't. But that's fine, because this gives us a very nice opportunity to apply what we've learned at the beginning of this video, right? And that will be our union function. Now, do note, this is union, not union all. If we said union all, we'll have quite a few more rows. We had 12 previously, we now have 17. And let's see, some are definitely doubled up. Here you go, 2 of mango, right? We don't want this, right? We don't need this. Yeah, these are doubled up as well. I think you get the idea, right? When you say union all, that doesn't remove duplicates. And in this case, because we don't want duplicates, we would simply just say union. And that gives us back everything. And those were joins. The key power here is the ability to insert rows despite the fact that certain columns may be null. A join is forgiving in the sense that it doesn't require everything to exist before we can actually bring them together. If there's nothing there, that's fine, we'll just attach nothing. We won't actually lose a row because of that. We're almost done, but before we do that, let's move on to the most complex thing of all, nested queries. Now, I do want to point out that this example is pretty contrived. Well, I mean, most examples we've seen kinda are. But yeah, bear with me, right? This example will show you that, well, there is a little bit of power here that again, we cannot express with just the basic Cartesian product. Or rather, we could, but there may be other problems. Let's take a look. For this part, let's do something completely different. But to keep things simple, we'll now confine ourselves to just one table. Now, here's the deal. What I want to do now is I want to find everything that is cheaper than grapes. So we have our grapes here, they're going for 110. And the idea is I want to find all the rows that cost less than it. Now, the twist here is that I don't, already know beforehand that grapes are 110. And what that means is I need to find out from the database first how much the grapes cost. Then I could compare myself against everything else to figure out, what's actually less. Now, there are several ways to approach this, and we can start off by doing just a very naive version. Essentially, when we do things this way, what we are saying is, we want to start off by creating a Cartesian product of the same table with itself. Now, if I remove the where clause just to show you how big this table is, look, we have 81 rows now. Because we have 9 rows in fruits and we are multiplying it by itself, we end up with a very huge table. So right off the bat, you can see a problem here already. Of course, we can now filter, right? We can say in the first table, I only want grapes. So filter out all the rows that are not grapes. This gives me the prices. And what I want then is a further filtering step to say that the stuff in B must have a price that costs more than the stuff in A. Now, since we only have grapes left in A, so yeah, this will be a comparison against grapes. I think earlier on I said less than, there was a correction, right? I think I meant more than instead because that's what I have here. But it doesn't matter, right? At the end of the day, it's just a comparison. Anyway, I run this, and there you go. The only things that hang around are the things that cost more than or equals to the price of grapes. That's why we also have grapes here, and everything else that costs more. So, okay, that's fine, that's great. But, like I said, we are creating something not so desirable here because we're doubling up on the same table. With this example, you don't really see the issue with it, right? But what if you're dealing with large amounts of data? That is going to put a lot of stress on your database. So you don't want to do that. There must be a better way. So between the sort of not so efficient answer and the best possible answer that we could create for this part, let's first look at sort of an intermediate answer between the two, right? This one, looks something like this. It uses a different kind of join called the inner join, right? This is greater than. I clearly didn't prepare this very well. But yeah, you get the same set of results. Now, before I jump into explaining this, I want to preface that how this is actually implemented by our actual DBMS, of course, varies from one DBMS to another. On some DBMS, ultimately for an inner join, they still perform a Cartesian product and then filter it down, just like how we would do it if we did it, ourselves, right? So in that case, there is really no performance improvement. In some cases, when they see inner join, they will try and optimize things. So in certain DBMS, you will see, slightly better performance. We are not going to worry too much about it. We're just going to try and understand the syntax and go from there. What we're trying to say here is that, we have a table called fruits. We're going to call it A. We're going to join it on the same table, but we're going to join it on, right? In other words, we'll only join it when this condition is true. And this condition says that from our second table B, the name must be grapes. Clearly, a DBMS that's capable of optimizing this operation will not generate an entire huge Cartesian product containing things that don't fulfill this condition. So if your DBMS checks this first, it filters down the table first before performing the product. As a result, you get a slightly more optimized performance. But of course, like I said, this isn't guaranteed. Regardless, this is definitely nicer syntax than we've seen previously. So yeah, this is the inner join method. But let's now take a look at one last way of doing this, in which we are basically guaranteed that, the right thing will happen. And that is one that uses a nested query. The query looks something like this. Now, that's a bit intimidating, so let's break this down slowly. I think the first thing you'll observe is that, look, we've got a select on the outside as usual, but we also have a select on the inside. In fact, we have a complete SQL query here. This is an instance of nested queries. We have a small query here inside our big query, and we're doing a small query that feeds its results into the larger query on the outside. Alright, so this is a little bit confusing. We're going to break it down bit by bit. Right, so let's start from the outer query. Now, the outer query isn't too difficult. The idea is, again, I want to perform a selection, I want a name and a price. The selection will come from two tables, the fruits table itself, which we'll call A, and this thing. Ignore what this is first, treat it just as a table called grape price. So we assume, right, before we look at this, right, we assume that we have a table that just contains the price of the grape. Then we simply filter it down so that a.price, which is our fruits list, is greater than grapeprice.price, right? So if we run this, we will still get the same set of results. So now we can look at the magic that's happening in here. This inner query is just doing another selection. It's going to our fruits table again, we call it B this time, and we'll get the price where the name is grapes. So what we've created here is basically like, you can imagine it as a new temporary table. It contains just the price of the grape. So when we put this as part of a larger selection, essentially we are just bringing two tables together. This is all the fruits, and this is really just a single cell containing the price of the grape. The Cartesian product is being formed between these two tables, but because this is essentially just a single row, you end up with the same number of rows. In fact, if I don't filter this down, right, and I just select everything, you'll see. Right, essentially, I have name and price. This is just the original contents from my table. And now what I have here is another price entry, which is just the price of the grapes. Notice, I didn't do any filtering on the final result. But because this only gives me just that one grape price on its own, I'm already looking at a minimal number of rows. In fact, this is what will happen for the inner join if it was optimized correctly. Right? Essentially, we do the filtering first on our second table before we perform the join. Doing it this way means we don't create 81 rows and then filter it down. We filter it down before joining, and therefore we will only ever have 9 rows. So that is the idea of what's going on here. Now, if I were to undo my way back, right, just put everything back here and I run this again. There you go, right? These are the items that cost more than or equal to grapes. So that is the idea of a nested query. And of course, you can have a nested query in a nested query. You can have multiple queries that contain nested queries that you can union together. You get the idea. Based on the tools we've seen today, you can express very complex queries, and you can sort of string them all together very nicely. And there you have it. You can now work with multiple tables using, a bunch of different ways. And yeah, with this newfound ability, what you can do is you can form far more complex queries. In fact, the reason why I'm doing this episode is because recently I've been dealing with a fairly large amount of data, and it's all stored in an SQLite database. It is literally megabytes of data, and while that doesn't sound like much, remember, it's all plain text, so megabytes of plain text is a lot. I could technically form queries any way I wanted, but the problem is, well, queries now take a very long time to evaluate. We're talking about, say, hundreds of milliseconds, which is, while not bad, still not great, right? There is some noticeable latency there, which is not great. However, by using things like joins, you can drastically reduce the workload that, well, your DBMS needs to go through. And because of that, the timings pick right up. By just using a join statement, I have been able to, well, optimize a query that took about 250 milliseconds, that's about a quarter of a second, to something in the range of 20 milliseconds. That's faster than it takes for one frame of this video to appear on screen. So yeah, while some of these things may seem to overlap with the basics that we already know, these tools exist because it's far more convenient to express things this way. This tends to be better than, using the naive way, generating a whole bunch of rows and then filtering it down from there. So yeah, these are, well, good skills to have. Give it a try, right? And hopefully, you can start to get familiar with how these operations work. That's all there is for this episode. Thank you very much for watching, and until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.